Welcome back, students. Today we will be studying about the kinetic theory of gases. Today's video lesson will be about the basic assumptions in kinetic theory of gases, and apart from this we shall derive an expression for pressure exerted by a gas and thereafter understand what is kinetic interpretation of temperature. A gas is a collection of a large number of molecules which are in continuous rapid motion. The gas molecules have a size of the order of 2 angstrom. Ordinarily, the distance between the gas molecules is of the order of 2 nanometer. This means it is about 10 times as large as their size. Therefore, the gas molecules can be considered as to be moving freely with respect to each other. However, during motion, when they come close to each other, they suffer a change in their velocities due to the intermolecular forces. Therefore, such changes in velocities of the molecules of a gas are due to molecular collisions. Rudolf Clausius and James Clerk Maxwell developed the kinetic theory of gases in order to explain gas laws in terms of the motion of the gas molecules. The theory is based on some assumptions as regards to the motion of molecules and the nature of the gases. The basic assumptions are: number one, all gases consist of molecules. The molecules of a gas are all alike and differ from those of other gases. Second, the molecules of a gas are very small in size as compared to the distance between them. The molecules of a gas behave as perfect elastic spheres. Third, the molecules are always in random motion. They have velocities in all directions ranging from 0 to infinity. During their random motion, the molecules collide against one another and the walls of the containing vessel. The collisions of the molecules with one another and with the walls of the vessel are perfectly elastic. Next, between two collisions, a molecule moves along a straight line, and the distance covered between two successive collisions is called the free path of the molecule. Next, the collisions are almost instantaneous. That is, the time during which a collision takes place is negligible as compared to the time taken by the molecule to cover the free path. The molecules do not exert any force on each other except during collisions. So this is the basic assumption in kinetic theory of gases. Now, next we shall study about pressure exerted by a gas and kinetic interpretation of temperature. As told in the kinetic theory of gases, a gas exerts pressure on the walls of the containing vessel due to continuous collision of the molecules against the wall. Consider a gas contained in a vessel. Now we are done with the labeling part. Once again, suppose that the edges OA, OC and OE of the vessel are along X, Y and Z axis respectively. Let n be the number of the gas molecules per unit volume, and m be the mass of each molecule. Let v be the velocity of any gas molecule at any instant. So if Vx, Vy and Vz, Vx, Vy and Vz along x, y and z axis respectively be the components of velocity vector v, then we may write down v square equal to vx square plus vy square plus vz square. Now the molecule moves with momentum mvx. The velocity is vx and mass of the molecule is m, so it moves with the momentum mvx along the x-axis and strikes against the face ABGF. ABGF. While moving along the x-axis, it hits the face ABGF. Now, since the collision is perfectly elastic in nature, the molecule rebounds back with same speed Vx. As the direction of motion is reversed, the momentum of the molecule after the rebound will become minus of mvx. It will rebound with a negative value of mvx, minus mvx. Therefore, change in momentum. Let's find out. Change in momentum of the molecule along x-axis. So that will be equal to minus mvx, that is minus twice of mvx. Now let us find the change in momentum of the gas molecule hitting the area A of the face ABGF in time delta t. Now, in this time delta t, all these molecules will hit the area A of the face ABGF, which lie in the cylinder of length Vx delta t and area of cross section A. Therefore, such molecules lie in volume A Vx delta t, that is area into length A Vx delta t. Since the number of molecules per unit volume is small n, so the number of such molecules that is lying within the cylinder should be n multiplied by the volume, so n Avx delta t. In fact, on the average, half of this number is expected to move along negative x-axis and the other half towards the face ABGF along positive x-axis. Therefore, we may write the number of molecules hitting the area A in time delta t along positive x-axis will be equal to half n into a Vx into delta t. Therefore, the total change in momentum of molecules in time delta t along x axis, if we denote it by delta px, that should be equal to minus of 2m vx into half n a vx delta t, and on solving this we get minus mn into a vx square delta t. Now, different molecules or even the same molecule at different times may possess different velocities. Therefore, in this expression for delta px, it is reasonable to replace vx square by the average value, that is the mean square component of the velocities of the molecules along x-axis. Therefore, replacing vx square by square, that is mean square component of the velocities, what shall we get? Delta px to be equal to minus m into n a v bar x square into delta t. Now, the rate of change of momentum is called force from Newton's second law. Therefore, force exerted by walls of the vessel on the gas molecules along x-axis will be Fx equal to delta Px by delta T, and that is equal to minus mna v bar x square. Now, according to Newton's third law of motion, the gas molecules also exert an equal but opposite force on the walls of the vessel. Therefore, force exerted by gas molecules on the walls of the container, that should be equal to minus of Fx, that is equal to mna Vx bar square. So, if Px is pressure exerted by gas molecules along x-axis, then we may write down Px to be equal to Fx by A, force by area, that is equal to mna v bar x square divided by A So A and E get cancelled and you're left with mn v bar x square. Similarly, we can write down for the pressure exerted by gas molecules along y-axis, Py to be equal to mn v bar y square, and pressure exerted by gas molecules along z-axis, Pz, equal to this is m, and Pz will be equal to mn v z bar square. Now, since gas molecules have same properties in all directions, the choice of x-axis, y-axis and z-axis is arbitrary. In other words, pressure exerted by gas molecules is same in all directions. So we may write down Px to be equal to Py to be equal to Pz, and let this be equal to P. Therefore, P will be equal to 1/3 of Px plus Py plus Pz. So let us substitute the values for Px, Py and Pz. Taking out Mn as common, we get and this is equal to 1/3 mn v bar square, where v bar square is equal to vx bar square plus vy bar square plus vz bar square. It is the mean square velocity of the gas molecules. Now, as m into n, that is equal to rho, that is density of the gas. Therefore, P can be written as 1/3 rho v bar square. Now, once again, from the expression for pressure equal to 1/3 mn v bar square, if we write down P to be equal to 2/3 n and then half m v bar square. So obviously half m v bar square is equal to average kinetic energy of gas molecules. So we can write down P to be equal to 2/3 n into average value of kinetic energy. Now, if n is total number of gas molecules in volume V, then we may write down small n to be equal to n by V. Once again, we can write down pressure as 1/3 m n by V into V bar square, that is further equal to 2/3 into n by V into half m V bar square. Therefore, PV is equal to 2/3 times n into average value of kinetic energy. Or we may also write down P to be equal to 2/3 times half rho v bar square, where half rho v bar square is the average kinetic energy of the gas per unit volume. Now, let us find out kinetic energy of a molecule and of 1 mole of a gas. Consider 1 mole of a gas. If P, V and T are the pressure, volume and temperature respectively of the gas, then by perfect gas equation we know that PV is equal to RT. Now if M is the molecular weight of the gas, then we can write down rho to be equal to M by V. So obviously from the expression for pressure we know that 1 P is equal to 1 by 3 rho V bar square, which can be written as 1 by 3 M by V bar square. So that implies PV to be equal to 1 by 3 M V bar square. So now PV is equal to RT and PV is equal to 1 by 3 M V bar square. So we can equate these two equations and hence we obtain 1 by 3 M V bar square to be equal to RT. Therefore, average kinetic energy of 1 mole of a gas, that is half M V bar square, is equal to 3 by 2 RT. Now this equation gives mean kinetic energy of 1 mole of the gas. Now 1 mole of the gas contains molecules equal to Avogadro's number. So if M is mass of one molecule and N is Avogadro's number, then capital M can be written as small m into N. So now the above equation can be written as half into Mn into V bar square, and that is equal to 3 by 2 RT. Therefore, average kinetic energy of one molecule will be half M V bar square, that is equal to 3 by 2 times R by N into T. Now R by N is equal to universal gas constant per molecule of the gas. Okay, R by N is called Boltzmann's constant. It is denoted by small k and its value is 1.38 into 10 to the power minus 23 joule per molecule per Kelvin. So now we may write down half M V bar square to be equal to 3 by 2 K. So this equation gives average kinetic energy per molecule of the gas, and it may be noted here that it does not depend upon the mass of the molecule of the gas. So let's now understand what is kinetic interpretation of temperature. Now, from the kinetic theory of the gases, average kinetic energy of a gas molecule is given by half M V bar square that is equal to 3 by 2 times kT. So we can write down half mv bar square to be directly proportional to T. Thus average kinetic energy of a gas molecule is directly proportional to the absolute temperature of the gas. In other words, higher the temperature of the gas, more will be the average kinetic energy possessed by the gas molecules. Thus, the temperature of the gas gives the measure of the average kinetic energy of the gas molecule. Now, if T is equal to 0, then half mv square is also equal to 0. Therefore, absolute 0 is that temperature at which the molecular motion stops. So this is what we refer to as the kinetic interpretation of temperature. Thank you.